Hello students. Today the experiment that we are going to study about is the requirements for plant tissue culture laboratory. The aim of the experiment is to study about the requirements for plant tissue culture laboratory, media preparation, various sterilization techniques and inoculation techniques of different explants. The equipments required for the experimentation include autoclave, pH meter, magnetic stirrers, magnetic beads, weighing balance, laminar airflow, etc. And the materials required include salts and vitamins of Murashige and Skoog's medium, that is MS 1962 medium, sucrose, agar, conical flask, measuring cylinders, and beakers of various sizes, reagent glass bottles, spatula, tissue rolls, distilled water, cotton plugs, aluminum foils, 1 normal sodium hydroxide solution, 1 normal hydrochloric acid solution, myo-inositol, autoclavable polybags, Borosil glass test tubes of the size 150 into 25 mm, preferably without rim, black marker pens, micropipettes, micropipette tips, test tube stands, etc. Let us first learn about the laboratory requirements for plant tissue culture. The first requirement is the general organization. The basic organization of a laboratory for a plant tissue culture laboratory requires 3 areas. First, general laboratory or media preparation area. Second, transference area or the area for the aseptic manipulation of plant material, and culture rooms with controlled conditions for light, temperature and humidity for maintaining cultures. The second requirement is high purity water. High purity water like double glass distilled water or deionized water are used in tissue culture procedures. Water should be used immediately and stored water is not preferred. The next requirement is glassware. Glassware used for tissue culture should be washed with laboratory detergent and rinsed several times with tap water, followed by a final rinse with purified water. Glassware should not be mixed with those used in other experiments, since toxic metal ions absorbed on glasswares can affect the cultures. The next requirement is plant material. Healthy and actively growing plant materials are commonly used in tissue culture. Contamination rate is lower in explants derived from disease-free greenhouse plants, as they can be easily surface sterilized. Explants can also be derived from in vitro germinated seedlings, as they produce contamination-free plants. The next part of the experimentation is media preparation. The culture media supply the entire essential mineral ions required for in vitro growth and morphogenesis of plant tissues and are composed of a mixture of macronutrients, micronutrients, vitamins, amino acids or other nitrogen supplements, sugar or carbon source, other undefined organic supplements and growth regulators or plant hormones. Plant tissue culture media may be either solid or semi-solid or liquid medium. Solid or semi-solid medium contain solidifying agents or support systems like agar, while liquid medium lacks agar. Let us now see the general methodology for preparation of medium, which is MS medium in the present case. Murashige and Skoog or MS medium is the most commonly used basic media in plant tissue cultures. Let us start with the preparation of stock solutions. The first is the mineral stock. Stock solutions of the mineral salts excepting iron and EDTA are made as 100 times stock containing 100 times the concentration specified for MS medium by grouping the compounds by the ions they carry as nitrates, sulfates, halides and PBMO or phosphorus, boron and molybdenum. Table 1 shows the list of stock solutions for minerals of MS medium made at 100 times final concentrations. The amounts corresponding to 100 times concentrations of these minerals were taken and dissolved in 1 liter of double distilled water for each type of stock solution. Stocks are stored in amber bottles and kept at 4 degrees Celsius after labeling them, and 10 ml of each stock is used to make 1 liter of the medium. The next is iron stock. Stock solution of iron EDTA complex is prepared at 100 times concentration by mixing 2.78 gram of ferrous sulfate heptahydrate and 3.74 gram of sodium EDTA together in 1 liter of double distilled water and heating it gently until the solution becomes orange colored. Stock solution is then transferred to an amber bottle, autoclave, levels it and then stored at 4 degrees Celsius. 10 ml of the stock is used in 1 liter of medium. The next type of stock solution is the organics stock. Stock solutions of nicotinic acid, thiamine hydrochloride, pyridoxine hydrochloride and glycine are prepared as 50 mg per 100 ml of distilled water and stored in an amber bottle at less than 4 degrees Celsius. 1 ml, 0.2 ml, 1 ml and 4 ml of nicotinic acid, thiamine hydrochloride, pyridoxine hydrochloride and glycine stock solutions respectively are used in making 1 liter of medium. Myo-inositol at a concentration of 100 mg per liter is generally added fresh. The next type of stock solution is the plant growth regulator stock solution or PGR stock. Stock solutions for each growth regulator is prepared by dissolving the plant growth regulator in double distilled water in the ratio of 1:2. For example, 5 mg of plant growth regulator in 10 ml of double distilled water. The cytokinins are first dissolved in a little amount of double distilled water, adding a few drops of 1 normal ICl, while auxins are first dissolved using a few drops of 1 normal sodium hydroxide if required. The solutions are gently warmed and the volume is brought up to 10 ml with double distilled water. Stocks are stored in amber bottles at 4 degrees Celsius. Next, let us see the steps involved in preparation of the medium. For making 1 liter of media, about 500 ml of double distilled water is taken in a 1000 ml conical flask and keep it on a stirrer after adding a stirring bar. 10 ml each of the nitrate, sulfate, halide, PBMO and iron EDTA stock solutions and the required amount of the organic stocks are then added to it. Then weigh 30 gram of sucrose and dissolve it in the solution by stirring it. After dissolving the sucrose, the flax is brought down from the stirrer and the volume is made up to 1000 ml by adding double distilled water. The pH of the medium is then adjusted to 5.8 by using 1 normal hydrochloric acid and 1 normal sodium hydroxide. 8 gram of agar is then added to the solution after warming it by keeping the flax on a hot plate at 60 degrees Celsius. The solution is stirred continuously with a glass rod until the agar dissolves completely, forming a clear solution. To this medium, the required volume or volumes of plant growth regulator stock or stocks are added and the 20 ml or 70 ml of the medium was then dispensed in culture tubes of the size 32 into 200 mm or flask of 250 ml Erlenmeyer flask respectively. Kept them with cotton plugs made of non-absorbent cotton. The culture vessels containing media are sterilized by autoclaving at 121 degrees Celsius for 20 minutes. After autoclaving, the flasks are taken out and cooled by keeping them on a rack while the culture tubes are kept on slants on the rack, and these are kept for 2 to 3 days before use to see whether contamination appears. Contamination appears if the medium is not properly sterilized. Next, let us see the aseptic techniques or sterilization techniques. Sterilization refers to any process of destroying or removing all infectious organisms, including endospores and viruses. Plant tissue culture technique involves culture under aseptic condition and requires the exclusion of invading microorganisms during experimental procedures. The various sterilization techniques used in plant tissue culture procedures are as follows. The first technique is wet heat or autoclaving. Media and apparatus are sterilized by autoclaving at 15 pounds per inch square or 121 degrees Celsius for 15 minutes. Autoclaving uses pressurized steam to kill microbes, spores and viruses by hydrolysis and coagulation of cellular proteins. The next technique is filtration. Filtration is an alternative sterilization technique for heat-labile substances. Filters made from heat-fused glass particles or membrane filters made from cellulose esters with an average pore diameter of 0.2 micrometer is normally used for removal of bacteria. However, viruses and phages can pass through these filters and filtration is not considered good option if these are a concern. The next technique is dry heat or flaming or baking. Instruments like forceps, spatula, scalpel, etc. used in aseptic transfers can be made sterile by flaming. Flaming the opening of receiving vessels prior to transfer also reduces contamination. The next is the use of laminar airflow cabinet. Laminar airflow cabinet with horizontal airflow from the back to the front and equipped with a Bunsen burner is the primary equipment used for aseptic manipulation. In the laminar airflow cabinet, air is drawn in electric fans and passed through HEPA or high efficiency particulate air filter such that sterile airflow through the working place flows in direct lines, that is laminar flow. the working surface is cleaned with 70% alcohol before starting any experiment. The next technique is irradiation. UV lights may be used to kill organisms in workbenches like the bench of Laminar airflow cabinet, in which aseptic manipulation of cultures are carried out. However, it should not be turned on while any other work is in progress, since UV light of some wavelengths can damage eyes and skin. The next technique is surface sterilization. If explants are not from aseptic sources like tissues from in vitro grown seedlings or cultures, then surface sterilization procedures are employed to remove surface contaminants from the explant tissues. Common chemicals used as sterilizing agents with their effective concentration and exposure time are given in the table. Antibiotics in the concentration of 4 to 50 mg per liter can also be used for 30 to 60 minutes. Let us now see the inoculation techniques of different explants. Inoculation is the transfer of plant materials used as explant to tissue culture medium. Inoculation of explants is carried out under aseptic or sterile conditions as follows. First, place the plant material still in the surface sterilizing container, the containers of sterile water, the sterilized forceps and blades, and tubes containing sterile medium in the sterile workbench of the laminar flow cabinet after cleaning them with 70% alcohol. The gloves are also sprayed with a 70% alcohol solution and hands are rubbed together to spread the alcohol prior to placing hands into the chamber. Now carefully open the container with the plant material and pour off the surface sterilizing solution. Then pour sterile water into the container and replace the lid and gently shake the container to wash the explants for 2 to 3 minutes. Pour off the water and repeat the washing process for at least 3 more times. Next, remove the surface sterilized plant material from the sterile water with the help of a forceps and place on the sterile petri dish. Cut the explant into smaller pieces using a scalpel handle with a sterile blade. Now open the tube containing the medium and flame the mouth of the tube. Then take a piece of the sterile explant with a sterile forceps and place into the medium in the tube. Replace the cotton plug tightly on the tube and place the culture on racks inside the growth chamber. Let us now see the results. A well-set semi-solid medium without contamination after 3 days of preparation was suitable for use as the medium for inoculation of explants. The surface sterilized explants inoculated on the culture medium remained green and increased in size after 1 week in culture, indicating successful application of surface sterilization and inoculation technique. Thank you.